I have the voltage on the capacitor in the circuit given by this equation. Okay, this is just a simple capacitor circuit equation where you have the resistor, a capacitor, a source. And then this is the voltage across the capacitor. And you can derive that equation, and you have derived that before. Okay? And I'm going to make RC equals 1 to make life simpler. And I'm going to make the right hand side a cosinusoidal function is equal to cosine of omega t. I ask myself what the particular solution should be. Okay? And to find a particular solution, I make a guess that is something of this form. If the right hand side is cosine of omega t, then the particular solution must also be cosinusoidal, but with a phase shift. Okay? Now if we plug this particular solution to the left hand side, I have the left hand side being omega p, sine of omega t plus theta. Okay, that is what I get for the first term. If I differentiate this, I get a sine. If I differentiate, I get an omega coming out, plus p cosine of omega t plus theta. And this must be equal to cosine of omega t. And what trick do I do now? I convert the right hand side to make it look like the left hand side. So I say that this is omega t plus theta minus theta. Okay? And then I would have this being equal to cosine of omega t plus theta, cosine of theta, plus sine of omega t plus theta, sine of theta. Okay? The right hand side becomes like that. Now I can balance the term and compare the coefficients. I must have minus omega p being equal to what I have over there, sine theta. I must have p being equal to, what should p be equal to?
Should there be a minus sign?
Do I have a minus sign there?
It's minus.
Cos A minus B is cos plus sine sine. Cos A minus B is cos plus sine sine. So this should be a plus sign. If I remember my trigonometric identities well. Okay, he agrees with me. He agrees with me, so I must be correct. So what should P be in this case? Compare the right hand side with the left hand side. Cosine theta, right? If you look at this term over here, this must agree with this term over here in order for them to be equal. So P must be cosine theta. And I have to solve for P and theta. To solve for theta, I divide the two equations. When I divide the two equations, I get 10 theta. If I divide this equation by that equation, I get 10 theta equal to minus omega. Previously, we got minus omega over RC or something like that. But then we make our RC equals 1. So we just get this simpler equation. And then to get our P, what do? We square the two equations and add them up. Right hand side adds up to 1, right? You know that sine squared theta plus cosine squared theta equals 1. It's something that you should remember and commit to memory. Okay, so I would get the fact that omega squared p squared plus p squared must be equal to 1. I get these two equations, I find my theta, I find my p, and I have this problem solved. Okay, I find my particular solution. Not completely solved. After having found the particular solution, I write down the general solution, which is the sum of the homogeneous solution plus the particular solution. The homogeneous solution must be a constant times e to the, what is a homogeneous solution to this problem? Negative t, right? That is a homogeneous solution if my RC equals 1. Okay? Then the general solution then is just the homogeneous solution plus the particular solution which we have found to be equal to that, and you have found your theta and your p, for instance. Okay, so I can write this as p cosine of omega t plus theta. Okay, you know how to find your p and your theta. And then you write your a in a very suggestive form. So the a has the value of the initial condition built in. The initial condition given for this problem is that v of 0 minus is equal to 0. But this is a capacitance problem. Can v really jump? Cannot. Okay, because in the capacitor, I is going to see dv dt. This cannot have a jump discontinuity. It cannot jump. If it jumps when you differentiate it, it goes to infinity. Okay, when you see an equation like this, this can jump. The value of the current can jump, but the value of the voltage on the capacitor cannot jump. Otherwise, it gets some ridiculous answer for this equation. So this must also be equal to v of 0, must also be equal to v of 0 plus. It must all be the same. 0 is the value right at the origin, 0 minus is the value right before it, and then v of 0 plus is the value after it. Okay? So we can write Vt in a more suggestive form, V0 minus the particular solution at 0. Okay, this is a continuous function of time plus this particular solution as a function of time. I just call this Vt of t. You can write my Vt in this manner, and it will satisfy the initial condition. That when you set t equal to 0, that expression equals to v of 0. And then you know that this is 0. This is given to be 0. You plug this in, and then you can get the solution that you want. Okay? You get a solution that you want. Okay? Are there any questions regarding this?
Would you have two values of p?
What is that?
You'll have two values of p. How do you choose which one?
I don't have two values of p. What do you mean?
Plus or minus?
Oh, I have two values of p. One being plus and one being minus. What shall I do with that? I will pick the plus one. Okay, I will pick the plus one to be the particular solution. Because what Aditya is saying is that if I solve this equation, I get p squared is equal to 1 over omega squared plus 1. And then p is equal to plus or minus square root of 1 over omega squared plus 1. Which value should I pick? Should I pick the plus value, or should I pick the negative value? Plus, right? Is your guess. Why? Okay, there's an ambiguity here. That's a good question because you do not know what value to pick. To confirm, you do a back substitution. You take the plus sign, back substitute to see if the equation is satisfied. You pick the minus sign, you back substitute, it's not satisfied. It turns out that the plus sign is the one that would satisfy the equation. Okay, you do it by back substitution. Yes. You have a question?
So for the v h t is equal to a e to the negative t?
Yes.
Why isn't it e to the negative little a t? Like
Oh, because the equation that I have simplifies with this form. A becomes 1. So in general, this is the equation for that. But the textbook, when they did this example, said RC equals 1.
Okay.
It's a little bit confusing. I don't like that. I like the fact that they don't set RC to 1. Then you can see it in the equation. But once you set RC equals 1, it disappears from that equation.
So this might be a good question. So RC is equal to a, little a?
1 over RC is the letter A in that section of the textbook. Because that section of the textbook rewrote this equation with something that looks something like this. Plus AB T is equal to B F T. So if we compare this equation with what equations we have derived before, RC is leader 1 over RC is leader A. Okay? So this is rather complicated, but I think you can handle it, right? Trigonometry is not very difficult if you remember all your formulas. Trigonometric identities. Okay? I think I'm not supposed to go to 3.2.1, right? So if I'm not supposed to go to 3.2.1, then 3.4.1. So I have some time left, which is good news, right? I think I can finish the rest of the section in the next lecture, so I can leave the rest of the time for questions if you want to. If you have any questions, yes.
For the question 3.19 here, so the homogeneous part is equal to y, equal to like y negative 1, which is 0, minus the particular solution at negative 1 when the solution is 0. Why we bother to times why we still need to times the like exponential something?
Oh, because the general solution is written in this manner. Let's review that part again. If you have a ODE, let's take this to be the ODE that we have. The ODE has a general solution which consists of a homogeneous solution, which is written by this plus particular solution. This is a general solution. Okay? What I've done is to write A in a suggestive form so that A becomes very indicative of what the initial condition of the problem is. So I write A as B of 0, say B, I can call this particular solution, okay? Particular solution at 0, e to the minus t over RC plus B particular of t. I've just rewritten my constant A into the difference of these two terms. So that when I set t equal to 0, this term cancels that term. And if I set t equal to 0, this just becomes that. If I set t is equal to 0 in this expression, I get this expression. Can you see that? T is equal to 0 here, I get 1 here. I get this term canceling this term, I get this term back. So I'm just redoing the same thing here. I wrote this constant in front in a suggestive form, so that when I set t equals to minus 1, this in fact will evaluate to y of minus 1. This is just a clever way to write this constant. Okay?
I mean, like 0 minus the particular solution at that point is already equal to the homogeneous solution, right?
No, this is a constant. This term here, entire thing, is a constant. Let me just say it again. Okay? This entire thing is just a constant times e to the minus t. This entire thing times e to the minus 1 is a constant times that. So the first term, no matter how I write it, is still the homogeneous solution. And then that second term is the particular solution. This is y particular, this is y homogeneous. Okay, the first one is just a clever way to write the homogeneous.